Hey Saxon Math, Algebra 1, we're going to start with Lesson 5 in this video, and we're going to be talking about finding absolute value and adding real numbers. First of all, let's kind of come up with some of the vocabulary terms that we're going to be using in this section. So the first term that's important to us is this idea of absolute value. And absolute value is the distance from zero. So if I were to consider these two numbers, say -4 and +4, when I consider those numbers, I can think about them in terms of their distance from zero. And so if I have -4, and these symbols are called the absolute value symbols, these straight lines on either side of -4. If I have -4 and I want to consider its absolute value, what I'm really saying is how far is it away from zero, and that's 4 as indicated here. Same thing with +4. If I put them in those absolute value bars or that absolute value symbol around it, what I know is that the absolute value of 4 is 4 because the distance from 0 is 4. So with the concept of absolute value out of the way, let's take a look at some of these examples at the bottom. So what's the absolute value of 0? How far is 0 from 0? Well, it's no units away, so it's 0. How far is 7.12 or 7 12 from 0? Well, that's just going to be 7.12 or 7 12 because the absolute value is the distance and it's negative, never negative. Sometimes I'll refer to the absolute value bars, those bars we just talked about, as almost like a positive maker. Anything inside the absolute value bars, once you've done whatever math needs to be done, will be made positive. Let's take a look at part C with that in mind. So in part C, we're doing 1 minus 3 over 4. Don't go changing the minus sign to a positive sign. First, you have to do whatever work is inside, and no matter what answer you get within the absolute value brackets, we are going to make sure that the answer turns out to be positive. So 1 minus 3 over 4, to me, I'm thinking 4 over 4 minus 3 over 4. And I know that's 1 over 4. So this can be written as what's the absolute value of 1/4? And we know that's 1/4. Similarly, over here, we're going to deal with what is in the parenthesis, or what is within the absolute value symbol first. 11 minus 2, we know to be 9. So this is the absolute value of 9 with a negative on the outside. That's significant. If we have that negative on the outside, that negative is along for the ride. But the absolute value of 9 itself is 9. So our ultimate answer is -9. Hopefully that made sense when you read through it. If not, look at it again or make sure you take a moment to ask me. Let's move on to the next example. At the bottom of page 23, you'll see just a precursor or prerequisite information for example 2. You'll see that the rules for adding real numbers are basically if you're adding a positive number and a positive number, your answer is going to be positive. Just add and keep the sign the same, right? Negative plus negative, just add and keep the sign the same. So the abbreviated way that I'd write that is when adding same sign numbers, just add and keep the sign the same. So that's what we're figuring out in here. And now if we look at this next one, if we're adding numbers with different signs, we are going to subtract those two numbers. We're going to subtract the two numbers, and your answer is going to take the sign of the number with the greatest absolute value. Sometimes we just say the bigger looking number. So for instance, if you're looking at this problem here, 3 plus a -2, since 3 looks bigger, is kind of the bigger number, it's the one that's furthest from 0. Since 3 is bigger, the answer is going to take that sign. Over here, since 3 is bigger over here, the answer will now be negative, so the answer takes that sign. So it takes the sign of the bigger looking number or the number that's furthest away from 0 or the number with the greatest absolute value sign. So again, here we're subtracting. All right, so with that, let's talk about example 2. So example 2, we're adding two numbers with different signs. We know that the answer is going to be positive here. We're going to subtract, and our answer is going to be a positive 9 because 21 minus 12 is 9. Over here, -19 and a -8, since both signs are the same. Remember, when both sides are the same, we're just going to add and keep the sign the same. So we're going to end up with a -27. Let's go ahead and look at a couple of other examples. Over here, we're dealing with numbers that are not integers, they're rational numbers, but the idea is the same. We can see that this is the number that is furthest away from 0. The signs are different. We will be subtracting, and our final answer is going to be negative. In fact, a negative 1.9. Next thing we're looking at over here is adding two numbers that are negative. They're fractions. The denominators are the same, so it makes life really easy for us. We're just going to add them. Remember, we don't add the denominator of our fractions. We just add when the denominators are the same. We only add the numerators, all right? So this is what we get. Feel free to let me know if this is making sense when you get a chance to watch the video, and we can talk about it. If it doesn't, let's look at example 3. So for this section, we are looking at an example 3, identifying whether a set is closed under addition. Now, you remember we talked about closure in sets, meaning if I add elements from that, if I'm talking about closure over addition, if I add elements from that set up, will the result also be in that set? So the first question we're asked is the set of integers closed under addition? So we remember what integers are. They're those number line numbers, right? So 0, 1, 2, 3, going in the positive direction, -1, -2, -3, so forth and so on, right? So if I add up any of these two numbers, will I also get as a result a number line number? Think about it. Will I get an integer? For me, the answer is yes. This is a true statement. So I don't have what they're asking for, which is a counterexample. This is a true statement, and that's what the text said here. The statement is true because the sum of any two integers will always be an integer. Well, let's try this next one. The set of real numbers is closed under addition. Real numbers now. This is 1.1, 5.5, all the things. Every number we can think of. That can be written as a fraction or a decimal that's repeating or terminating. What do you think? 1.2 plus like 5.7. Yeah, I guess that's going to be a real number, right? All of the examples we can think about are going to be real. And so this also is going to be a true statement. And so that's what the text tells us that is true. Let's look at example 4. So here we're using a real life situation in order to demonstrate how negative and positive numbers work. On the first down, the Cougars lost 4 yards. They gained 7 yards. On the second down, use addition to find the total number of yards lost or gained on the first two downs. So the first down, we had a loss of 4 yards, so we're going to call that -4. And then we gained 7 yards, we're going to call that +7. And then when we think of the overall change or the overall situation, we realize we're adding two numbers with different signs. We're going to subtract and take the sign of the higher number. So we end up with a +3, just as the text does here. The Cougars gain a total of 3 yards on the first two downs. With that in mind, let's go ahead and make some time to work on the lesson practice. Do all of these, which is really going to reflect the work we just did in the examples, and then continue on to work on the practice. Do as much of these as you possibly can, as they are going to give us real opportunity to practice some old concepts. What I also want you to notice is that they will tell us where this comes from. So you see SB3, this comes from the Saxon course back in the day, course number 3, and this comes from section 2. And so you can kind of use that to assist you if you need a little bit more help. All right, talk to you soon. Bye-bye. All right, so here we are at Saxon Math, Algebra 1. We're going to talk about Lesson 6. We're going to be subtracting real numbers. And we have a little new concept that we're going to talk about, which is the additive inverse. And it's this idea that there are numbers, when you add them together, you're going to get 0. And you've seen this before, I am absolutely sure. So let's go ahead and highlight this idea. Opposite numbers are considered additive inverses, and they're opposite because when I add them together, they're going to kind of cancel each other out, and we're going to get 0. So 5 plus a -5 would be an example of adding two opposites or demonstrating the idea of additive inverse. So the reason why our text chose to show that is because what they're going to have us do is to change a subtraction problem like this. Ooh, that's too much there. Change this subtraction problem into this situation by using the additive inverse. The way I've talked about this before and the way other teachers have talked about it before is that when you have subtraction, you're going to keep the first number the same way it is. You're going to change the sign to addition, and then you're going to change this number to its additive inverse or just to the opposite. So sometimes we'll say keep, change, change. If I'm in a particularly silly mood, I might say don't do. Don't do. Don't change this, do change this, do change this. So 3 minus 5 after don't do or keep, change is going to be 3 plus a negative 5. 3 plus a negative 5, we already know how to do that because we know to subtract the two numbers and take the sign of the higher. And so we would end up with a negative 2. Let's take a look at a couple of practice problems. So if you see down here, we're going to work on some practice problems by doing a little bit of a rewrite first. We get negative 12 plus a negative 21. Don't change the first one. Do change this. Do change this. Now we're just adding two negative numbers, and we know how to do that. We just add and keep the sign the same. Rewrite over here in part B would leave us with a negative 19, plus a positive 8. Do you see that? Don't, do, or keep, change. So we kept it the same, changed it, and changed it. When we're adding two numbers with different signs, we subtract, and we take the sign of the bigger looking number, the one furthest away from 0, the one with the greatest absolute value. So that's going to be the 19. So our answer is negative 11. You can see that here. Let's go ahead and take a look at the next section or the next few examples. We're actually subtracting. We're going to change it to addition. We've got 3.2. I'm going to change that to a plus sign, and I'm going to change this to a positive 5.1. Look at life. This is so much easier. So we're going to add these together, and their signs are the same. So I know our final answer will be positive, and I'm going to end up with an 8.3 when I add 3.2 and 5.1. Let's handle this over here. The rewrite's going to be simple. Negative 3/5 plus a positive 1/5. The signs are different. We're going to subtract and take the sign of the number that's furthest away from 0, the number that looks bigger, however you want to say that, and we get negative 2/5. Let's take a look at the next example. So here in example 2, we're going to be talking about closure again. Remember when we talked about closure, the idea that if I do something to a set, then that operation will always produce elements that are either in the set. If that happens, then we have closure. If we don't have that, then we don't have closure. So let's think about it. The set of integers, we know number line numbers, is closed under subtraction. So if I were to take any of those numbers on the number line and add and subtract them, not add them, but subtract them, would I get an integer? And so you can just try a couple, negative 6 minus a negative 1. If we do a little keep, change, we're going to get that, and we'll get a negative 5. And after you do a couple of these, you realize that indeed we are closed under addition, or it's closed over addition, because any two integers, when we subtract any two integers, we're still going to get an integer. So this is a true statement, we would say. And let's consider this next one. The set of real numbers is closed under subtraction. So if I have real numbers, so fractions, decimals, and I subtract them, will my answer still be a real number? And the answer is yeah, that's also true. And that's what your text is talking about in this section. Let's look at example 3. Here in example 3, we're looking at an application and we're thinking about dive depth. And so we have Nayib, who collected a water sample at a depth of 23 meters from the surface. So that's 23 meters down. Let's make 23 out of that. There. So 23 meters down from the surface, and then he descended another 12 meters to collect a plant sample. Where was Nayib in relation to the surface when he retrieved the plant sample? So I'm going to think about this as subtracting going down 12 meters. But from what we talked about, we realized that the negative 23, we can also consider adding another depth or an additional depth of 12 meters. In either case, we're going to be adding these two numbers together to get 35, and we know our answer is going to be negative because both numbers are negative and we just add and keep the sign the same. So we know that this gentleman is negative 35 feet from the surface when we end the problem. Make sense? All right, you guys know the deal. We've got lesson practice to work on, and then you have some extra practice review problems to check out. All right, let's go ahead and get to work, and I'll talk to you soon. Okay, take care. Here we are with lesson 7. We're going to be talking about simplifying and comparing expressions with symbols of inclusion. So when we refer to symbols of inclusion, we are talking about symbols of inclusion are going to refer to like a fraction bar, absolute value symbols, parentheses, and braces or brackets. So they all kind of give us a way of thinking about focusing our attention. So if you had a fraction bar, we had like 4 plus t over x. You know that the 4 plus t in a way could have a parenthesis around it because that's one whole thing. That's one separated set of numbers in a sense. And we know these other ones, the absolute value, the parentheses, the brackets. Sometimes these brace kind of things you might see they are inclusion. They kind of group numbers together. All right, so with that in mind, let's think about looking at example 1. So let's take a look at example 1 and check out what's going on. We have a symbol of inclusion, which is these absolute value symbols. And that reminds me, those symbols of inclusion are kind of like part of our Please Excuse My Dear Aunt Sally. Remember that? Or PEMDAS, where we know the order in which things should be done. That P refers to those symbols of inclusion. So we need to go to that first. So the first thing I'm going to do is rewrite this problem, but I'm going to deal with this. What is 4 minus 6? It's negative 2. Okay, but this is the absolute value of negative 2, which is going to be a positive 2. So my final answer is going to be 9 minus 2, which is going to give me 7. So the answer to this is going to be a positive 7. Let's take a look at this one here. We have 5 times 2 plus all of this stuff in brackets. Let's deal with the brackets first. Look at my rewrite. 5 times 2 still come into play. I'm still going to deal with this 3 here, but I'm going to deal with this most inner bracket, this most inner situation of inclusion. 6 minus 8, I could do 6 plus a negative 8, but I think 6 minus 8 is going to ultimately give me a negative 2. This is not absolute value sign, so I'm not going to change it to a positive 2. I'm going to keep going. Notice I'm rewriting everything, and I'm going to deal with this now. So the next thing is to add 3 plus a negative 2, and within this bracket, I'm going to get the number 1. You guys see how I'm getting that? Because 3 plus a negative 2, subtract, and I get 1. So now my problem is 5 times 2 plus 1. I'm going to now focus on multiplication, and that's going to be 10 plus 1. Finally, my answer is 11. All right. Hopefully that's good. Let's go ahead and move on to the next example. We're going to look at example 2. So example 2 reminds me of the last couple of examples, but a little bit more involved. I'm going to rewrite this problem 3 plus 5 times, and now I'm going to deal with what's inside the bracket. So what's in the brackets here? 9 minus 3 is going to give me 6, and I'm raising that to the second power. And so I still have to deal with what's going on inside of the bracket. Look at my rewrite. 6 squared is 36. I've got to deal with that. And now I get 36 minus 6. I'm in the bracket, still focusing on the bracket. 3 plus 5 times 36 minus 6 is 30. So this becomes 30. That bracket is no longer necessary. And so now, given order of operations, I'm going to have to multiply before I do this addition. So 3 plus 5 times 30 is 150. And then I get 153 as my final answer. So another example where we got a lot more involved is this guy. So here's a couple things I want you to observe. When we've got this fraction bar, you can almost assume that there's like a parenthesis right here. So that's telling you to do that first, and then if there was like a bunch of numbers here of things that needed to be done, addition, subtraction, you would do this. So you want to make sure and treat these like parentheses too. Okay, with that in mind, let's go ahead and look at our problem. I'm just going to do a quick rewrite, and then we're going to focus in exactly where we need to focus. So if you had to start a problem like this, you want to work within the parentheses. You want to work exactly within those parentheses. So my first rewrite is going to be this whole thing here, but instead of having 4 plus 2, I'm going to make that 6 to the second power, close, and I'm just going to focus on one thing at a time. All right. So can put that there. And so now I'm going to deal with this. This exponent is within the bracket. I got to deal with my brackets first and deal with that which is inside. So 6 squared is 36. So this becomes 5 times 36. And then plus 4.5. 4 times 5 over 2 rather. And so I'm going to get started with that multiplication as well. So I've got 5 times 36. I can actually do that multiplication, which is going to get me 180. And then I'm going to multiply this and get 20 over 2 and then finish off the problem. Before I add, I'm going to do this division because that's really what's happening here. I get 10 and then 180 plus 10 is 190. And so that's going to be my final answer here. So this final example, I think this is the final one, we'll see in a minute, but this example 4, is using our less than, greater than, or equal to symbol to compare these two expressions with what I'm going to say is a whole lot going on. So basically what you have to do is simplify this as much as possible, which means you got to do the rewrite and simplify. So this is going to be 5 times 7 minus 5 is 2. To the third power minus 14. That's a little bit squeezed up there, but let me go ahead and write it neater. So I have 12 plus 5 times 2 to the third power. 2 to the third power is 8. And so 5 times 8 is going to be 40 minus 14. And let's go ahead and finish what's in the bracket there. We're going to end up with 40 minus 14 is going to end up being 26. And so now 12 plus 26, on this left side of the equation, we're going to get 38. And so we're comparing that to whatever happens down here. Let me go ahead and make that circle look a little bit better. And in this circle, we're going to put like either greater than, less than, or equal to. So let's go ahead and handle this. 9 minus 5 is going to give us a 4. So that's 4 quantities squared. And we're adding that to 7. And eventually we're going to subtract 3 to the third power. That's going to be 16 plus 7, which is going to give us a 33. Let me think. 16 plus 7 does not give us 33. It gives us 23. And then we're going to subtract from that 3 to the third power, which is 27. And when we do that, we end up with a negative 4, right? Because we'll plus this plus negative. We'll do keep, change, or don't do. And so having the 23, we'll leave that, we'll change that to addition, subtract the 27, we get a negative 4. And when I compare that, clearly 38 is greater than negative 4. The text seems to corroborate that story, and so we end up with this side being greater. Good. Let's look at example 5. So in example 5, we've got Beatrice who wants to buy 3 DVDs marked at $7 each and 4 CDs marked at $12 each. Everything in the store is on sale for half off the marked price. Beatrice has $31.50 to spend and a coupon good for $1 off each CD. Use the expression below to determine if Beatrice has enough money to buy all the items she wants. So what this is going to do is just, they gave us the equation, so we don't have to think as deeply as the problem initially seems to indicate. There's that $31.50 that she has, and we're subtracting. We've got the half off as indicated by dividing everything by 2. We've got that coupon for each of the CDs she buys. So 4 times 1 is going to give us the subtracted amount for each of that dollar off coupon. So everything is covered in here for us. It's just our job to simplify the situation. So what we're going to do is I'm just going to start my rewrite over here, $31.50. I'm going to subtract from that all this stuff in here. At the top of this, the numerator here, I'm going to write 21 over 2. And then over here, I'm going to write 48 over 2. And then I'm going to write minus 4. So that's just me simplifying things. And then I'm going to continue on, still $31.50. Let's simplify this a little bit. I can join like terms together, or I can join these fractions together, which is going to give me 69 divided by 2. And then I'm going to subtract 4. And when I have 69 divided by 2, that's going to be 34 and a half, I believe. Let me write it this way, 69 over 2 minus 4. And I think my number is right, 3150 minus, so I'm still dealing with this little section in here. Let me go ahead and highlighted so we can follow along. So that little bracket is what I'm about to work on in here. So if I divide 69 by 2, I'm saying I'm going to get that 34 and a half. And then I take that 34 and a half and I subtract 4. I'm going to end up with $30.50. I feel like I just did math magic. Let me unpack that just a little bit for you in case that was weird. So this over here became, remember, our $31.50. We're subtracting. Here's the pink bit in here. This is $34.50 minus $4. Okay, that's what we got. Then when we subtract that $4, everything was the same, except now this pink bit in here is now just $30.50. Right? $30.50. And so now that I've simplified that, you can see that at the end of the day, I'll be left with $1. So let me go ahead and scooch down here. I'll put my $1. So it does seem like we have enough for that. And we can check how the text did it. The text did exactly the same thing. And we see that we have $1. All right, so with that, we have reached the end, and our lesson practice is perfectly primed for you to get done. And of course, we've got the additional practice again to continue building your math muscles. I look forward to talking to you soon. Let me know if there's any questions or concerns, and I'll answer those. Please take care, and we'll get back to each other in the next lesson. Bye-bye. Hi, everybody. We're in section 8, lesson 8, and we're going to be talking about using unit analysis to convert measures. So let's see what that's all about. Okay, so when we talk about unit measures, we're talking about conversion factors or ratios as it were, that are going to be helpful in changing things from one unit to another. So for instance, one thing I want you to look at when we use these conversion factors, you got to notice that both of the values at the top and bottom are actually the same. They are equivalent. And if you think of it that way, you'll realize that you're not actually changing the value of the numbers that you're working with. You're just changing the form. You're changing the look. Because in essence, if you've got two things that are equal to each other and they're on top of one another as a fraction, you know that each of these really just equal the whole number 1. And when you multiply stuff by the number 1, you don't change its value, but you might change its look depending on the fraction you use. With that in mind, let's take a closer look at example 1. Okay, let's look at example 1. So we're going to be converting unit lengths. We've got a cheetah that ran at a rate of 105,600 yards per hour. That's not particularly a convenient way of discussing that kind of speed. So we can look at it as how fast did the cheetah run in miles per hour? That's a little bit more convenient. That's something we can think about a little bit easier. So we need to convert that. So here's what we do. We first start off by rewriting this as a ratio, 105,600 yards per hour. And so now we want to change these yards into miles. Here's what we're going to do. We're going to use a special conversion factor. That's a fancy number 1, right? We talk about conversion factors are really just number 1s. We're going to use a fancy conversion factor that's going to cancel out the yards and in its place put miles. So if you didn't know it, you know it now. If we have 1 mile is equal to 1,000. Let me see if I remember 1,732 yards. Let me see. Nope, lied to you. 1,760 yards. And so since we have this little fact here, we're going to write it as a conversion factor. So I can either write 1 mile over 1,760 yards, or I could do the reverse. I could write 1,760 yards over 1 mile. And both are fine, except one's going to be right in terms of helping us and the other one's not. So here's how I know. I want to get rid of the yards. So the yards can only cancel out if they're on a diagonal. So I'm going to put 1,760 yards in the denominator and 1 mile at the top. And then so when I'm done, I'm going to be canceling out those yards and I'll be left with miles, okay? So that's something that we sometimes get confused. These are both equivalent, which one to use. The reason why we use this one is because it achieves the goal that we're looking for. We want to cancel out those yards and get that mile. Okay, so with that in mind, let's go ahead and do the thing. So now that I've got my units to agree, when I'm done this math, I'm going to be totally in it with miles per hour. And so if I go through with it, I multiply across, I get my 105,600 at the top miles, right, per 1,760 hours. You see that little change that happened? By canceling out the yards, I created this new situation, which is true, but this is also inconvenient. I want this per hour. And so what I'm going to do is grab a calculator. Yes, I said it. I'm going to divide that because these are pretty big numbers. I know you can do long division. We're cool. Now I want you to just tell me what the rate is per hour, per 1 hour. And that would just be a little bit of division. And when we do that division, we end up with 60 miles per hour. All right, hopefully that made sense. And we can look at another example. All right, let's look at example 2. We're going to be talking about covering unit area. So a gym measures 8.5 centimeters by 14 meters. The owner bought mats to cover the floor, and each mat is 110 centimeters square. If 95 mats were purchased, are there enough mats to cover the floor? So there's a whole lot going on. Let's go ahead and think about what the deal is. First thing we'll do is we'll find the area of the gym. And then we're going to consider the area of the mats, the area that the mats will cover. Okay, and so that's the best way to compare this area that the mats will cover. All right, so if we think about those two things, first the area of the gym is going to be a little straightforward because we're going to take 8.5, we'll multiply it by 14. We're talking about meters here and meters here. And when we multiply them, I think we get 119 meters squared, okay, 119 square meters. And then when we come over to, well, we can continue with this. We're dealing with, each mat is 110 centimeters square. And I'll be honest, this is not clear to me what they're talking about. At first, I was like, wait a minute. So if the mat, I'm going to draw a picture of the mat. If the mat is said to be 110 centimeters square, so what they're saying is that this is supposed to be a square, my friends, that this side is 110 centimeters. So that's a little bit longer than a meter. So these squares, these mats that were purchased are a little bit bigger than a meter. So it's larger than a square meter. So now what we got to do is break this down and think about how many square centimeters are here and how many square centimeters are here. So that's going to be an interesting idea that we're going to pursue. Let me change gears and talk about what's happening on this side. Let's figure out what the area of the cover is. So the area of these mats would be 110 centimeters times 110 centimeters, right? That's giving me the number of little square centimeters that are there, and I got 95 of them. So I'm going to multiply that by 95. And when I'm done, the area is going to be a whopping 1,149,500 centimeters squared. So that's just how much the mats are going to cover. Let's see if that's enough for the space that we're dealing with. So we've got this. We've got 8.5 times 14 meters is going to give us 119 meters squared. But the next thing we need to do is see how many centimeters that is. So here's the conversion. We know that 1 meter is equal to 100 centimeters. So if we have 1 meter square, that will be 1 meter times 1 meter. We call that 1 meter square. But if we're considering the number of centimeters or square centimeters in that 1 meter square, we got to do 100 times 100, which is 10,000. So we're dealing with 10,000 centimeters square in each of the square meters that we're dealing with. So hopefully you realize we're going to take that 119 meters squared, we'll multiply it by 10,000 centimeters squared to calculate the centimeter squared. So this is how we are thinking about the conversion factor. So I would literally do this, but let's think about why this works as a conversion factor type of problem. So let me go back. So I know that here 1 meter squared is equal to 10,000 centimeters squared. So I'm going to write that as the number 1 in a fraction form like we did before. But notice I'm going to put the 1 meter squared at the bottom because I want those to cancel out. And I want my answer in terms of centimeters squared, which I know is 10,000 centimeters squared is equal to 1 meter squared. And so now I'm going to go ahead and multiply that through, crash, crash. My answer is going to end up being in centimeters squared, which is what I want because that's what's happening over here. And of course, I end up with 1,190,000 centimeters squared. And so because of that, we could see if we're comparing these two numbers that indeed we don't quite have enough, since this side is greater, we don't have enough of the mats to cover the space. So here in example 3, we're going to do an application of converting units of volume. So we've got a hose with a flow rate of 41,472 cubic inches per hour, and it's filling up a pool. The volume of the pool is 1,104 cubic feet. How many hours will it take to fill the pool? Okay, so we have a lot of information to consider here. First thing, I want to just point out that we have 41,472 cubic inches can be filled in an hour, okay? So this would be inches cubed, that's cubic inches, are going to be filled in 1 hour. So that's one time relationship we're going to need. The next thing is that the pool is 1,104 cubic feet, and we're going to write that as feet cubed. So I'm going to put that there. Now, the question is, how many cubic inches are in a cubic foot? We already know that 1 foot is equal to 12 inches. And so if we cubed both sides, basically raise them both to the third power, we get 1 cubic foot is equal to 12 to the third power, which is 1,728 inches cubed. So now that we can think about that, we can now consider what's going on here in terms of how many cubic inches we have. Let's break it down. So we know that our pool starts off with 1,104 cubic feet. We want to change those cubic feet into cubic inches because that's what makes sense given the fact that we know how many hours it takes or how many cubic inches can be filled in 1 hour. So that transfer is going to look like this. Look at this. We're going to use this relationship here. We're going to write it as a fraction, but we're going to write it as a fraction to get rid of what we don't want. We don't want cubic feet any longer. So I'm going to put 1 cubic foot at the bottom, and I'm going to put 1,728 inches cubed at the top. This is just a fancy number 1. I'm not changing the value. So then when I do my cancellation, I'm going to get a really large number here. But I'm not going to stop there. Let me get rid of that. I'm not going to stop there because after I change this, it's going to be changed into inches. Now I want to know how many hours it takes. So this little guy is going to give us another conversion factor. Now it's not quite the number 1, but it is in that I know that this is essentially equal to this. I know that 41,472 cubic inches is equivalent to inches filled is equivalent to 1 hour passing, okay? So I'm going to write a fraction out of this. 1 hour is going to go at the top because that's what I want. I want time. How many hours will it take for this to happen? And then in the denominator, I'm going to put 41,472 472 inches cubed because I want to get rid of that. So now that I set up my whole situation, I'm canceling out the units. I see when I'm done, I'm going to be left with hours. I know that my conversion factors are cool because they represent the data and information that I know to be true and the data information given in the problem. When I multiply this together, 1,104 times 1,728, and then I divide it ultimately by this in the denominator, 41,472, I get 46 hours. All right, I hope that made sense. Remember what we did. We used some facts. We said, okay, we started with this relationship. We recognized this one. We talked about this one over here. Let me circle that. We talked about this one over here. These relationships that I'm circling here, let me circle it in a brighter color. These relationships that I'm circling here in pink are what gave us these conversion factors. This one here and this one here. All right? Okay, let's go ahead and look at our last example for this section. Okay, so we are looking at a foreign exchange situation. Jared and his family are going on vacation in Europe and he takes $225 with him. He needs to exchange this amount for its equivalent value in euros. If the current exchange rate is €1 to $1.36, what is the value of Jared's $225 in euros? And this is a straightforward one. We're going to start off with $225. And we know that the relationship of dollars to euros is this. So €1 equals this amount of dollars. So I'm going to make my conversion factor, my fancy number 1 out of this fact. I want to get rid of dollars. So the $1.36 is going to be at the bottom and the €1 is going to be at the top. Are you with me? Hopefully that makes sense. So then the dollars, let me put a little dollar symbol here. The dollar symbols will cancel out, and then I'll be dealing with basically 225 euros divided by 1.36, and that's how many euros I'll get when I transfer them. So I'm going to calculate that real quick, and we get 165.44 euros, which were equal to 200, which is equal to $225. All right. I hope that made sense. I hope you're feeling comfortable with this. Go ahead, get the practice done, and I look forward to talking to you soon. Take care. Bye-bye, honey.